As software programs grow, they inevitably reach a crisis point. Without strict structural management, they collapse under their own complexity. Managing this chaos requires breaking the monolith down into a strictly controlled framework. This diagram outlines modularization, dividing a massive program into independent units. This creates a separation of concerns, allowing modules to handle specific tasks without interference. Isolated logic can be safely reused. Self-contained modules let developers track errors, collaborate easily, and expand securely. The core building block of this entire modular architecture, the single unit that makes scalable software possible, is the method. To understand exactly what a method is, we have to look past the syntax and define it in abstract terms. This systems diagram visualizes a method using the analog of a physical coffee machine. A method is simply a pre-designed tool with a strict contract for operation. Calling the method is like pressing the start button on the machine. You trigger the pre-built logic to execute. To perform the work, the method requires inputs, or parameters. By providing the size of the cap or the specific type of coffee, you dictate the exact variation of the task the machine will run. Inside the machine, the heating and mixing happens entirely out of sight. This represents implementation hiding. The caller does not need to know the internal mechanics, only that the logic executes correctly. Finally, the machine delivers the return value to the user, completing the cycle. Provide the correct inputs, and the machine guarantees the expected output. Developers can rely on complex logic without re-engineering it every single time. Let's map this physical model directly into actual code. This layout details the structure of a Java method, separating the code into 3 distinct anatomical parts. First is the header. This establishes the method's signature and its strict operational contract with the rest of the program. The header defines exactly how the method is accessed, the type of data it will return, its name, and the specific parameters it expects to receive. Below the header is the body. Wrapped in brackets, this is the isolated environment where the core logic, data processing, and calculations actually take place. This isolation creates what is known as variable scope. Any variable declared inside this body is strictly local, confined entirely to this one method. Local scope acts as a firewall. It ensures the method's internal math cannot accidentally leak out and corrupt data in other parts of the application. The final command inside the body is the return statement. This statement securely transfers processing control, alongside the final computed value, back to the main program that called it. Programmatic syntax functions as a structural boundary, enforcing the secure input, execution, and output of the underlying logic. The utility of any method relies on its adaptability to the data it receives. These code examples show methods constructed without parameters. They rely on empty parentheses and function as static triggers for isolated, repetitive tasks that do not require external input. In contrast, this Java code shows a method taking multiple parameters. The logic dynamically alters its calculation based on the exact combination of numerical inputs provided by the caller. We must also analyze the data flowing in the opposite direction. Developers are required to strictly declare what a method gives back to the system. This grid compares methods that return primitive data types, like integers or booleans, against void methods. A void return type explicitly states that the method performs an action, such as printing text to a terminal, but passes 0 data back to the underlying program. Parameters and return types are the dynamic levers that transform a rigid block of code into a highly flexible, reusable tool. When data crosses the boundary into a method, what is actually happening to the physical system memory? Systems utilize 2 distinct strategies to handle data transfer, ensuring memory conflicts do not crash the application. This chart contrasts the 2 approaches, starting with passing by value on the left. Passing by value creates a strict duplicate of the original data. Any mathematical changes occurring inside the method operate on the copy, leaving the original variable completely unaltered. Duplicating small integers is a safe practice, but duplicating massive, complex arrays is highly inefficient for a computer's memory. The solution for large data structures is passing by reference. Instead of duplicating thousands of variables, the system passes the exact memory address pointing directly to the original data. This efficiency introduces risk. Passing by reference gives the method the power to permanently mutate the original data outside of its local scope. This key takeaway clarifies a specific rule in Java. The language strictly passes primitive types by value, but for objects in arrays, the value it passes is the memory reference itself. Understanding how these memory states interact allows a developer to optimize for system performance without risking permanent data corruption. We return to our sprawling system, now fully stabilized because the code is partitioned by rigid modular boundaries. The method header enforces the strict communication contracts between these complex interlocking nodes. The method body isolates the execution logic, keeping the broader application uncluttered by internal processing steps. Variable scope and reference rules act as precise traffic controllers, ensuring system memory is manipulated safely and efficiently. Combining these principles allows developers to stack abstractions, building massive applications out of tiny, verifiable pieces. Developing these modular units signals the transition from simply learning language syntax to designing true system architecture.